Okay, so today's video is looking at solving trig equations. I'm going to start with today's video just looking at very simple trig equations. Very little complicated happening here at all. So we'll just get the sense of what's happening, and then in the subsequent video we'll have a look at solving harder trig equations where there's a bit more going on. Okay, so the first thing that we need to understand when we're solving trig equations is given that circular functions are periodic with a domain of R, equations involving circular functions have an infinite number of solutions. Well, the kinds of equations we'll be looking at anyway. So, for example, we're looking at the equation of sine of x equal to a half. If we think about that graphically, you'll remember I've said to you before now, any equation can be thought of graphically. It can be thought of as, where does the graph of y equals sine of x intersect with the graph of y equals half? That's essentially what the equation's asking us to do. So that's what we're seeing in the picture below. The blue line is y equals sine x, and the red line is y equals a half. And so therefore the points of intersection between those two lines are the solutions to this equation. So when we think about it this way, it becomes clear why we're going to get infinitely many solutions to this equation. Here in the picture, I'm seeing this over a domain from negative 6 pi to 6 pi, and within that domain we can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 solutions. That one over there is just past 6 pi. So there'll be 12 solutions to this equation over that domain. Over the domain 0 to 2 pi, there's only 2 solutions. So what we're going to look at here is solving trig equations with a restricted domain, so looking to find specific solutions. Quite a bit further on in this topic we will have a look at finding the general solution to this equation. So that would be finding a way to describe those infinitely many solutions. So we will also have a look at that. And some people actually prefer that as a method and prefer to find the general solution first and then from that solution find specific solutions. But we'll visit that in quite a few lessons' time. So for now we're going to focus on finding specific solutions within a set domain. Okay, this is something that we really need to see done and explained, solving trig equations. It's very hard to write a set of steps that you follow. There's a lot of information that you just need to be able to put together to all of a sudden be able to write down the answer. So you need good knowledge of your exact values. You need an understanding of the unit circle and the symmetries and where sine is positive and where cosine is positive, etc. Yes, and you need to be able to sort of put all that together all at once. So it can be difficult to just look at a written solution and see how that solution was obtained. But I'm going to attempt to give you a set of steps, but I won't claim that they're perfect, and they're a bit vague in their language. So the first thing is to rearrange the equation so that you have sine equals or cosine equals or tan equals, but we'll look at the tan equations separately down the track. Okay, so you want the sine or the cos on its own. Okay, any numbers being added on or multiplied need to be divided or subtracted over onto the other side. Then we're going to use our exact values to determine, now I've called it the basic angle here, sometimes you'll see it referred to as the reference angle. Okay, so what we're looking at here is using our exact values to decide which angle in the first quadrant are all of these solutions going to be related to. That angle in the first quadrant might not actually be a solution depending on your domain, but you're looking to find which angle in the first quadrant. Now because we're looking at exact values, we're really only looking at, it's either going to be pi on 3, pi on 4 or pi on 6. That's it. Okay, one of those three. Maybe pi on 2 or 0 in other equations as well, but essentially that's all we can deal with exactly by hand. So which of those angles are we dealing with? Then which quadrants are my solutions going to be in? Are my solutions in the second and third quadrant or in the third and fourth quadrant? And then thinking about, okay, what are those angles related to pi on 4? What is that angle in the third quadrant? What is that angle in the fourth quadrant? Whatever it might be. And then we need to use the domain to find all the required solutions. Now it's this fourth step, thinking about the domain, that gets much more complicated when our equation gets more difficult, so we're just starting off with these very simple equations. Okay, so again it all comes back to our unit circle. Draw the unit circle. Be really clear about what's happening here. Okay, so we're solving sine of x equals a half, 0 to 2 pi. Now we can see that on our graph up here. We could probably hazard a guess at what those two solutions might be. So we're actually looking at these two solutions in the first quadrant here, they're what we're trying to find between 0 and 2 pi. In the first period there. Okay, so what we want to think about, first of all, is step 1, making sure our equation is just sine of something is equal to something, which is what we have here, so we don't need to do anything at step 1. Step 2 is to use our exact values to determine what angle are we talking about here, what angle are all our solutions going to be multiples of. So this is where we need to either remember our exact values, or as I said to you in an earlier video, excuse me, I'm not an advocate for just remembering the values because you've got no way of knowing whether or not you've remembered them right. So I use the special triangles to generate them. Now I know that 1/2 comes from the special triangle that is half of an equilateral triangle. Okay, so half of an equilateral triangle of side length 2, which means that length is 2 and that length is 1. If it was an equilateral triangle, that makes that 60 degrees or pi on 3 radians, which makes that 30 degrees or pi on 6 radians, and if I use Pythagoras' theorem I can work out that this side length is √3. I just know that. That's the one thing I do remember. So I've chosen this triangle because this triangle has side lengths of 1 and 2, which means I'm going to be able to get a ratio of half out of this triangle. Okay, so we want sine to be equal to 1/2, which means that this 1 has to be the opposite and this has to be the hypotenuse. So therefore we must be talking about pi on 6 as our reference angle. So this triangle tells me that sine of pi on 6 equals 1/2. Okay. Alright, so you might say, okay, well we're done then. So that means that x equals pi on 6. But this is where the symmetry of the circular functions becomes a problem. So we know that our solutions are connected to pi on 6. Okay. We then want to think about which quadrants our solutions are in. So is sine equal to a positive or a negative value here? So in this instance, sine is equal to 1/2. Okay, so that's positive 1/2. So I think about a unit circle and I think about the fact that sine is the y coordinate, and so we're looking at where is the y coordinate equal to 1/2. Okay, so that means there's going to be a solution in the first quadrant and a solution in the second quadrant. Okay, now we've already established from our exact values what this first quadrant solution is. This angle here is pi on 6, which means that according to the symmetry, the angle up from here must be pi on 6, okay, which means that angle in the unit circle is pi minus pi on 6. Okay. The next thing is to use our domain to find the required solutions. So for this particular equation, our domain is 0 to 2 pi. So we're going to start here at 0, and we're going to be travelling around the unit circle. That's pi on 2, this is pi, this is 3 pi on 2, and this is 2 pi. Okay. So we're doing one lap of the unit circle going in this direction, and we're finding all the solutions in that one lap. So we see there are two solutions, here and here. This solution is pi on 6, and this solution is pi minus pi on 6, which is 5 pi on 6. You need to get good at doing that fraction work in your head. So what I'm doing in my head is I'm thinking, well, this is pi. Pi is 6 pi on 6. So therefore 6 pi on 6 take away 1 pi on 6 is 5 pi on 6. So my solutions here, x is equal to pi on 6 or 5 pi on 6, 5 pi on 6 within that domain. Okay, example 2 is the same equation. The only thing that's changing
Here's what I found.
is the domain. So the domain goes from being 0 to 2 pi in the example 1, and now it's negative 4 pi to 4 pi. Okay, so essentially we've already done most of the steps that we need to do here. So again, thinking through our steps, the function is already rearranged so that sine of something equals a number. Okay, our exact values we already did in part 1. We know that it's about pi on 6 when sine of x equals 1/2. Okay, which quadrants? We know that sine equals 1/2 in the first two quadrants, so quadrant 1 and quadrant 2. And so the only thing that's changing here is the domain, so that very last step that we just did. So let me just draw myself another unit circle here. I'm going to draw the circle a bit smaller to give me a bit more space around it. Okay, so we know that our solutions are related to pi on 6 in the first and second quadrant. So our solutions are going to be located here, and let me just try that again, here in circle. Okay, so pi on 6 up from the x-axis in both quadrants. Then we want to think about our domain. This is where things are different. So this time we're going from negative 4 pi to 4 pi. Now personally I find this much easier to think about the positive solutions first, so go from 0 to 4 pi, and then reset, go back to 0 and go do the negative solutions, go from 0 around to negative 4 pi. Okay, so let's do the positive solutions. We have already done 0 to 2 pi, so we're starting at 0, we're travelling around our unit circle to pi, to 2 pi, to 3 pi, and around to 4 pi. Okay, so from 0 to 4 pi, we're going to get 4 solutions. 1, 2, 3, and 4. Okay, now we've already worked out the first 2 solutions. This solution is pi on 6. This solution was pi minus pi on 6, which is 5 pi on 6. And then we're going around the circle again. So when we get around to this next solution in the first quadrant, that solution is 2 pi plus pi on 6. So 2 pi is 12 pi on 6. 12 pi on 6 plus another pi on 6, this will be 13 pi on 6. Travelling around to the second solution in the second quadrant, so thinking about 3 pi is 18 pi on 6. So 18 pi on 6, take away pi on 6 is 17 pi on 6. Okay, and so there's our 4 solutions. The other way you can do it, some people prefer, so my 4 solutions, let me just write them down, pi on 6, 5 pi on 6, 13 pi on 6, and 17 pi on 6. The other thing to note is the connection between these pairs of solutions. So obviously the difference from pi on 6 to 13 pi on 6 is just an extra lap of the circle. So you're just adding on 2 pi. So rather than figuring them out separately, once you find the first 2 solutions and then you go to the next solution, you think, I just need to do pi on 6 plus 2 pi. That's pi on 6 plus 12 pi on 6, which is 13 pi on 6. But that's basically what you're doing in the circle. I prefer the sort of in the picture, being able to see what's happening with the solutions. Again, the second pair of solutions, 5 pi on 6 is the first solution, 17 pi on 6 is a whole nother lap of the circle away from that, so that's 5 pi on 6 plus 2 pi. So you could do it that way, get your first 2 solutions, and then just add 2 pi to find subsequent solutions until you get to the end of your domain. Okay, so that's our positive solutions. Alright, now let's do that in reverse. Now I think it's going to be easier so you can see what I'm doing if I erase my positive solutions. Okay, try not to erase the important things. Alright, like the circle. Let's try that again. Okay, so alright, that'll do. There's a few things floating around, but we'll work it out. I'll use a different colour. So this time, we're going from 0 around to negative 4 pi. So negative angles mean we're travelling in a clockwise direction, not an anti-clockwise direction. So I'm going to use a different colour here, just so you can differentiate from those other markings I've still got left from the previous one. So we're starting here at 0. We're travelling this way around the circle, anti-clockwise. So this is negative pi around here. This is now negative 2 pi here. This is negative 3 pi here. And then this is going to be, let me move that negative 2 pi. That's negative 2 pi. And then we get here to negative 4 pi. Okay, so we've got different solutions here, obviously. So we need to be able to think. It's harder to think backwards. We've still got 4 solutions. 1, 2, 3, 4. Okay. So that first negative solution, this one here, is at negative pi minus another pi on 6. We're getting more negative, so we're subtracting. So negative pi, remember, is negative 6 pi on 6, minus another pi on 6, that's negative 7 pi on 6. Okay, travelling around to the next solution back in the first quadrant. So that's going to be negative 2 pi plus pi on 6. So negative 2 pi is negative 12 pi on 6. This isn't quite at negative 12 pi on 6. This is 1 pi on 6 less than that. or more than that I should say, so it's negative 11 pi on 6. Continuing around the circle, negative 3 pi, remember, is negative 18 pi on 6. So continuing further than that, this solution here will be negative 19 pi on 6. Negative 4 pi is negative 24 pi on 6. So this will be negative 23 pi on 6. Okay, so again, the other thing that you can do is, again, just starting from your two original solutions, pi on 6 and 5 pi on 6, would be to sort of start subtracting pi on 2 from there until we get to the end of the domain again. So our negative solutions are going to be, what have we said here? Negative 7 pi on 6, negative 11 pi on 6, negative 19 pi on 6, and negative 23 pi on 6. Now, it's nice if we wrote those all in order, but, you know, not necessary. But if we write them in order, from smallest to biggest, negative 23 pi on 6, negative 19 pi on 6, negative 11 pi on 6, negative 7 pi on 6, pi on 6, 5 pi on 6, 13 pi on 6, and 17 pi on 6. Again, each pair is just 2 pi apart. So pi on 6, we know we add 2 pi to get here. If we subtract 2 pi, we're going to get to this one. And if we subtract 2 pi again, we get to this solution. Okay, same here. 5 pi on 6, we add pi on 6, it's going to, add 2 pi, we're going to get to here. We subtract 2 pi, we'll get to this solution. We subtract 2 pi again, we'll get to this solution. Okay. Personally, I prefer the pictorial representation of it. I find it easier to sort of count in fractions. Okay, so it's 2 pi plus pi on 6, and it's 3 pi minus pi on 6, whatever it might be. Okay, let's have a look with some different numbers. Number 3. Okay, solve cos of x equals 1 on root 2 for x between 0 and 4 pi, so 2 laps of the circle. First step, cos or sine of something equals a number. That's all done. Second step is to think about our exact values. Okay, so our exact values here, again, I'm referring to my special triangles, and I know that there's no root 2 in the special triangle we used up here, so it's not in this special triangle, it's the other one. And so, as I said to you the other day, this triangle, I don't tend to need to draw this one. I know if root 2 is involved, it's going to be about pi on 4. Okay. Okay, so again, cos of something equals 1 on root 2, so adjacent over hypotenuse, so pi on 4. Okay, so my basic angle, or my reference angle, is pi on 4. And then I've got cos of x is equal to positive 1 on root 2. It's equal to a positive number, so therefore we're thinking about in which quadrants is cos positive. So remembering that cos is the x coordinate. So the x coordinates are positive in the first and fourth quadrants. Okay, so my reference angle is pi on 4. Try that again, so pi on 4 is 45 degrees, so it's exactly halfway. And then we're also going to have, solutions in the first quadrant if cos is positive. We're also going to have solutions in the second quadrant. In the fourth quadrant, down here, if cos is positive. Okay, then we think about domain. 0 to 4 pi, so that's 2 laps of the circle. So starting at 0, around to pi, around to 2 pi, continuing with a second lap to 3 pi, and continuing back around to 4 pi. Okay, so we're going to get 1, 2, 3, 4 solutions as we make those 2 laps around the unit circle. So that first solution we know is pi on 4. We got that from our exact values. The second solution is around here in the third quadrant at 2 pi minus pi on 4. So 2 pi is 8 pi on 4 minus pi on 4, so therefore this will be 7 pi on 4. The next solution, back in the first quadrant again, is 2 pi plus pi on 4. So that's 8 pi on 4 plus pi on 4, so that is 9 pi on 4. And again, around in the fourth quadrant, 4 pi minus pi on 4. 4 pi is 16 pi on 4, so minus 1 pi on 4 will be 15 pi on 4. You can also count your way around the circle. Pi on 4s are quite easy to count. So you're going to have 1 pi on 4, 2 pi on 4, 3 pi on 4, 4 pi on 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, it's just fractions, that's all it is. Alright, so our solutions then, x is going to be pi on 4, 7 pi on 4, sorry, that looks like a negative 7 pi on 4, but that's just hanging from my careless drawing there. 7 pi on 4, around again, 9 pi on 4, and 15 pi on 4. Again, if you prefer to just find the first two solutions and then add 2 pi onto each of those, that's all we're doing in the unit circle as well. Okay, number 4. This time we want to work in degrees. Now, it's not common that we're going to work in degrees. There's a couple of questions in the exercise, but I can assure you that in maths methods, we're really always working in radians. All the same, we should be able to apply the same process to a problem in degrees. So first step, remember, is to get the sine part of the function on its own. So we need to do some rearranging here. So we want to add root 3 to both sides. So 2 times sine of x degrees equals root 3. Remember we said if there's no symbol, no unit, it's assumed, the angle's assumed to be in radians, so we need to write the degree symbol when we're working in degrees. And so sine of x degrees is equal to root 3 on 2. Okay, so that's step 1. Step 2 is to identify our exact value. Now, thinking about our special triangles, I know that root 3 happens in the half and equilateral triangle. So sine is root 3 on 2, which means that root 3 needs to be the opposite, and 2 is the hypotenuse, and so that means I must be talking about this angle down here, which is 60 degrees, or pi on 3. So all my solutions are going to be connected to pi on 3. Again, we're looking at sine is equal to something positive here, so we know sine, the y-coordinate, is positive in the first and second quadrants. So we're looking at 60 degrees, so I wrote pi on 3 in my triangle, but we're working in angles, aren't we? So we want 60 degrees in the first quadrant and 60 degrees, try and get that a bit more symmetric, and 60 degrees in the second quadrant. Okay, so that's the location of all of our solutions. Now we want to think about the domain. Which particular ones do we want? So negative 360 to 360. So that's 2 laps of the circle, one positive, one negative. Again, I'm going to do them separately. I'm going to think about the 2 positive solutions. So starting at 0, heading off this way around the unit circle. So this is going to be 180 here. And this is going to be 360. Okay, we get 2 positive solutions. And then if we also think about the negative lap, so starting at 0, travelling this way around the unit circle, this is minus 180 and minus 360. Okay, so we've got 2 positive and 2 negative solutions. Sorry, 2 positive and 2 negative solutions. Technical issues, my apologies. Alright, so 2 positive and 2 negative. So the 2 positive solutions, the first one's nice and easy, that's 60 degrees. The second one is 180 minus 60, so that's 120. The negative solutions, okay, so remember we're travelling in a clockwise direction, so the first negative solution, so travelling back from 0, is negative 180 minus a further 60, okay, so that's minus 240 degrees, and then the one in the first quadrant is negative 360 plus 60, so that's minus 300 degrees. Alright, so we've got our 4 solutions. So x degrees is going to be equal to, let's list them in order, negative 300 degrees, negative 240 degrees, 60 degrees, and 120 degrees. 4 solutions. Okay, last one. Solve root 2 cos of x equals 1. Okay, so again, let's get the cos on its own. So root 2 times cos of x equals negative 1. Sorry, plus 1 equals 0. I read the equation wrong earlier. So cos of x equals negative 1 on root 2. Okay, again, 1 on root 2 has to be to do with pi on 4 because it has to come out of this triangle here, and it's only about pi on 4. So cos of pi on 4 is 1 on root 2. So my reference angle, basic angle, is pi on 4. Cos is negative, so we want to think about cos being the x-coordinate, where that's negative. So x-coordinates are negative in the second and third quadrants. So we're looking at an angle related to pi on 4 in the second quadrant and an angle related to pi on 4 in the third quadrant. Remember, we're always talking about symmetry from the x-axis, although in the case of pi on 4, it's the same thing, so it doesn't really matter. Okay, so that's the location of our solutions. Then we want to think about our domain. Nice simple domain this time, just from 0 around to 2 pi. Okay, two solutions. So this first solution, so this is pi here, and we're dealing with pi on 4, so this is pi is 4 pi on 4. Okay, so this solution is going to be 4 pi on 4, take away pi on 4, so that's 3 pi on 4. This one's going to be 4 pi on 4 plus pi on 4, so that's going to be 5 pi on 4. You could also just count. Okay, so just count in quarters. Okay, pi on 4, 2 pi on 4, 3 pi on 4, 4 pi on 4, 5 pi on 4, 6 pi on 4, 7 pi on 4, 8 pi on 4. Okay. Alright, so my two solutions, x is equal to 3 pi on 4 and 5 pi on 4. Okay. Before we finish up, just quickly solving trig equations with your CAS. So let's just take this equation here. If I was going to solve, so menu 3(1), solve square root of 2 times, square root of 2 times cos of x, oh, I'm in degree mode from my year 10s, just let me fix that, plus 1 equals 0 for x. Before I hit enter, I'm just going to change my angle mode. So clicking on the battery, document settings, radian mode. So if I just hit enter here, it's going to give me this. This is the general solution. We'll talk more about this. There's nothing broken about this. That's giving you a way of describing the infinitely many solutions, and we'll look at how to be able to do that ourselves. But we don't want all the solutions. Pressing Control Enter won't help here. That'll just give you approximate decimals, but there's still infinitely many solutions. You're getting that strange notation because there isn't a unique solution. So we need to tell it about the domain if we want specific solutions. So I've just scrolled up and I'm going to press enter to copy that again. So I need to give it the domain, and I do this using the given that symbol. And what's really important, the one place that everybody goes wrong here, and I don't know why, is that you cannot change what goes inside the solve function. The solve function, solve bracket, equation, comma, x bracket. That doesn't change. If we want to add a restriction, that happens outside the solve function. So close off the bracket at the end of your solve function, Control equals to get the given that symbol, okay, and then you want to put your domain in here. So 0 less than or equal to x, which is less than or equal to 2 pi. And now we get our specific solutions that match the ones we found by hand. Okay, time for you to do some practice.